Entropy and the second law of thermodynamics is going to be the topic of this lesson. We'll start off with more of a description than a definition of entropy before we get straight into the second law of thermodynamics. We'll talk about what it says, what it means, different ways it can be phrased, so that you really get a good understanding. And then we'll go back and return to entropy. We'll give a little more of a definition both to entropy as well as an entropy change and how to calculate it under a couple different situations. And we'll complete the lesson talking about heat engines, thermal efficiency, and the Carnot cycle. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start off with a little bit of a discussion of entropy, probably the least understood of the major thermodynamic properties. Now, we typically tell freshmen in a freshman physics or chemistry class that it's related to disorder. And it's important to remember that it's related to disorder. It's not the same thing as disorder. Systems that tend to have more disorder or randomness tend to have more entropy, and vice versa. So it's not the same thing as disorder. If I said that entropy is disorder or is randomness, that's not quite true, but in a sense it's some measure of disorder or randomness. And we'll take that right into the second law of thermodynamics, and the second law of thermodynamics describes what's true of entropy for a spontaneous process. And so we'll start off right there. So we'll say for a spontaneous process, and I'll stop there for just a second. So what in the world is a spontaneous process? And so a spontaneous process is one that happens naturally without any outside interference, without any work being done on a system, so to speak. So if I let go of this marker, it should naturally want to fall to the ground. So that is the spontaneous process that would result. Now, could it rise up to the ceiling? Well, not without some outside help. Now, I could hit it and cause it to rise up to the ceiling, but without any outside interference, that is not what would happen. That would be a non-spontaneous process. Well, again, the second law of thermodynamics addresses these spontaneous processes, and it says that for any spontaneous process, so the entropy, if I can spell entropy, that would be great. Entropy of the universe, and that's important, increases. So it's the entire universe. Any spontaneous process, the entire universe is going to increase in entropy. And this is important because it doesn't mean we can't get some sort of localized decrease in entropy. But for the entire universe, the overall entropy of the universe will indeed go up. All right, a couple different ways we could phrase this. They're always going to start off by talking about, referencing that it's for a spontaneous process. But another way we could talk about the universe here is we could talk about the change in entropy, and so S is the symbol for entropy we'll use here. So the change in entropy of the universe is going to be positive. So another way of saying that the entropy is increasing. If it's a positive change, that means it's going up. And then finally we could say one more thing. We could take that universe and divide it into two parts. The one thing you're looking at, we call that the system. So we could talk about the delta S of the system. And then everything else in the universe we call the surroundings or the environment. I'll call it the surroundings. And that combination is also going to have a change that is greater than zero. So just the delta S of the system, there's nothing that says that can't actually be negative. But by the time you account for the delta S of the rest of the universe, the surroundings, and I can't spell surroundings either, that's great. Let's get that U in there. By the time I account for that, the combination of the two is going to end up being positive. Now, it turns out we also are going to talk a little bit later about what we call a reversible process. And a reversible process is one where it's not really spontaneous. It's carried out under equilibrium conditions throughout. And you just kind of barely nudge it along, and it's kind of more of a theoretical construct than something we can actually achieve in practice. But for a reversible process, it turns out that is the one time where delta S here is going to equal zero. For the universe, yet again. You're never going to see delta S being negative for the universe, but either positive for any spontaneous process or zero for any reversible process. So, and the idea that it's reversible is the idea that you can get right back to the same state you started at, and that's only possible if you can get your entropy of the universe right back to where you started. Well, if it's carried out as a spontaneous process, you're never going to get back there because the delta S of the universe is going to be positive. But if you carry it out as a reversible process, that's the one time where the delta S of that process would be 0. And we'll reference this at the end of the lesson when we talk about the Carnot cycle. So now we want to get into one of our working definitions for entropy, or rather entropy change anyway. And it turns out that delta S is equal to Q reversible over T for temperature. So in this case, Q reversible just refers to the heat either emitted or absorbed by a system in a reversible process. And again, recall, we just said a reversible process is one that's kind of carried out under equilibrium conditions all the way through. And again, they don't really exist, but if you just kind of barely perturb the system out of equilibrium to kind of nudge it along all the way through the process, it gets really close to being this theoretical reversible process. So, but that's what delta S is, Q reversible divided by the temperature in Kelvin at which it's carried out at. And so we can see that the SI unit here, so for Q that's joules, and for temperature that's Kelvin, and so the SI unit for entropy is the joule per Kelvin. Now we want to go back and look at a couple of the processes we looked back in the last lesson. So isothermal either compressions or expansions, as well as adiabatic ones as well, and we looked at those for ideal gases. We want to look back at what we derive for Q so that we can kind of apply this and come up with an expression for delta S as well. So now the isothermal one's kind of the more interesting result, but the adiabatic one's the easier one to start with. So we'll start there. And if you recall, an adiabatic process is one where it's completely insulated. There's no heat transfer in or out of the system. And so Q is 0. And if Q is 0, it's pretty easy to see that delta S here is going to come out to equal 0 as well. So cool. Now the one that's a little more challenging, but not too bad, if we recall that for an isothermal expansion or compression of an ideal gas, that Q is equal to negative W, which came out to positive nRT, natural log of V final over V initial. And because it's isothermal, it's carried out at constant temperature, and so that temperature is a constant. And so if we take Q here and just divide it by temperature, we'll see that temperature is just going to fall out. And so that delta S is just going to equal nR natural log of V final over V initial. So not too bad. So and the reason we want to focus on these two is we're going to reference back to this when we talk about the Carnot cycle at the end of this lesson. Now there's one other situation we want to talk about, at least delta S for. I don't really care about Q too much, but that's for heating. So when you're heating something up, its temperature is changing, and because its temperature is changing all of a sudden, it turns out that the real definition here for delta S involves taking an integral. So, and as long as we've got a nice simple integral, it turns into this right here. So, but if we're actually going to take this integral with respect to temperature, well, it turns out when you do this upon heating and the temperature is changing, you're going to be taking the integral of 1 over temperature, so 1 over T dt, which involves a natural log, and that's why we're going to get a natural log here for delta S here. And so it turns out that delta S for heating so is N C ln T final over T initial, or N is your number of moles. So C here is your molar heat capacity. So, and then finally natural log of the final temperature over the initial temperature, and that'll get us delta S for the system. Now keep in mind, we talked about the second law of thermodynamics and talked about the delta S of the whole universe. These right here are just expressions for the delta S of the system, not necessarily the delta S of the surroundings or the universe. So just keep that in mind. If we write delta S and we don't label it, almost always we're referring to delta S of the system. If we're going to talk about delta S of the surroundings or the environment, we'll label it accordingly. If we're going to talk about delta S of the universe, we'll label it accordingly. But if it's not labeled, odds are it's the delta S of the system you're looking at. And if you're in a chemistry class, it might be the delta S of the reaction you're looking at. That might be the system of interest. So these are expressions for delta S that we might have to use in an isothermal expansion or compression or upon heating. And this technically doesn't even have to be for an ideal gas, as we'll see here shortly. So now that we've introduced some equations for calculating delta S, let's apply one of them. So a question here says 1.00 moles of water at 20.0 degrees Celsius is mixed with 1.00 moles of water at 80.0 degrees Celsius in an insulated container. Calculate the entropy change for the process of the mixture reaching thermal equilibrium. So the cold water is going to get warmer, the hot water is going to get colder till they're at the same temperature. Assume water has a constant heat capacity, Cp equal to 75.38 joules per mole Kelvin. All right, so let's map out what's going on here. So we've got 1 mole of water at 20 degrees Celsius. It's the cold water. We've got 1 mole of water at 80 degrees Celsius. So, and we're going to mix these together and let them reach thermal equilibrium in an insulated container here. So we're going to end up with 2 moles of water. We've got to find that final temperature when they reach thermal equilibrium, which is not so bad to do here. So because I've used equal amounts of water and they're really going to meet exactly in the middle temperature-wise. And we can see that they're 60 degrees apart, and so if they meet in the middle, so one will go up 30 degrees and one will go down 30 degrees to meet right at 50 degrees Celsius, which will be our final temperature. Now in this case, if we hadn't used equal amounts and it wasn't so obvious what that temperature was going to be, we'd have to, say Q of the hot water plus Q of the cold water adds up to 0. So, and we then go back and calculate NC delta T for each of these, where delta T is T final minus T initial. And the initial temperatures are different for these, but they'd meet at the same final temperature. We could calculate it out. But in this case, not necessary with the numbers being nice, and that's kind of the point. And the question then is, what is delta S for this process? And we're going to calculate it in 2 parts. We're going to calculate it for the 1 mole of 20 degrees Celsius water going up to 50 degrees Celsius, and for the 1 mole of 80 degrees Celsius water going down to 50 degrees Celsius, and then add the 2 together. Let's see how this plays out. So in this case, we've got delta S equals N, so 1 mole, times the heat capacity, Cp given is 75.38 joules per mole Kelvin. So, and then times the natural log, T final over T initial. And so in this case, we've got to put these in Kelvin. So as a ratio, notice if we did like 50 over 20 here, that would not be the same thing as the ratio in Kelvin. The ratio has definitely got to be in Kelvin here. So in this case, T final over T initial, so 50 plus the 273.15 is going to get us 323.15 Kelvin all over 20 degrees Celsius, so 293.15 Kelvin. Now, if we do the same thing here for the hot water, still got 1 mole, still got the same heat capacity, which we were told to assume to be constant. The truth is, heat capacity does change as temperature changes, but not a ton. So not a bad assumption to assume it's constant here in this case, and we're told to do it. So, and the natural log of T final over T initial. And it gets important that you identify T final and T initial. It's not just higher temperature over lower temperature. It really is final over initial. And so the final temperature for this one is also that 323.15 Kelvin. But the initial temperature of 80 degrees Celsius and 273.15 plus 80 is 353.15. All right, we now let our calculator do some work for us. All right, so 75.38 times the natural log in parentheses of 323.15 divided by 293.15. Close my parentheses, and we're going to get 7 to 3 sig fig 7.34 joules per Kelvin. Okay. And now same thing for the hot water. In this case, again, 75. In fact, I'm just going to use the same entry and go back and just change the temperatures. So it's still 323.15, but over 353.15. And now we're going to get negative 6.69 joules per Kelvin rounded to 3 sig figs. Cool, and if we add these two together, we'll get the delta S of the entire process. So again, plus 7.34, and it's going to be 0.648. A little dyslexic there, so 648. Let me just look back at that. Yeah, 648 joules per Kelvin. All right, so this is an important result here. So if we take a look at this, delta S came out positive. So with this container being insulated, so we're not considering the entire rest of the universe. There's only two parts to the universe we're looking at, the cold water and the hot water, and the overall delta S of the process comes out positive. And it turns out this is why heat is transferred from something that's hot to something that's cold, because you'll end up calculating a delta S that's positive, according to the second law of thermodynamics. If what actually happened was heat was transferred from the cold to the hot, and the hot would get hotter and the cold would get colder, what you'd find out though is that when you go to calculate delta S for such an imaginary process, the delta S would come out negative. It would be a violation of the second law of thermodynamics. And so really we're just verifying what we already know to be true, so that heat is transferred from hot objects to cold objects and not the other way around. And it corroborates what we know of the second law of thermodynamics. So we'll take a look at one last definition for entropy, and one that's a little more of statistical relevance. So looking at probabilities. But entropy is equal to the Boltzmann constant times the natural log of the number of microstates here, where W represents the number of microstates. So what in the world is a microstate? Well, a microstate is just one of the equivalent ways in which a system might exist. And oftentimes we can define it in terms of like energy is pretty common and things of the sort. So what does this mean? Well, we talked about mixing hot water and cold water just a second ago. And so the hot water, those average molecules have higher kinetic energy, whereas with the cold water, those molecules had lower kinetic energy. And once we mix them together, what's the most likely thing to happen? Well, we saw that heat's going to get transferred from the hot to the cold. Well, why? Well, at a kind of a molecular level, what's going on here is that as they mix together, you're going to get more equivalent microstates associated with more disorder, for the energies kind of having a broader smear of possible energies and things of this sort at some intermediate temperature. Whereas if we looked at the opposite and said, actually, we got all these high average energy molecules and low average energy molecules, and we're going to say that actually the higher energy molecules are going to get even higher and the lower ones are going to get even lower, because heat's going to get transferred from the cold to the hot, which doesn't happen. But that would be an even higher ordered system with more even higher energy molecules and more even lower energy molecules. So instead of a random smattering of some intermediate energy. And so that's kind of what's going on from a statistical kind of molecular level and stuff like this. All right, so to kind of demonstrate what's going on with this equation here, we're going to take a look at a non-scientific example of just rolling a pair of dice. So in rolling a pair of dice, and we're going to consider rolling a 2 versus rolling a 3 with that pair of dice. Now, if we consider rolling a 2, there's only one way this is going to happen. So, and that's if both die roll a 1, exactly. That's the only way they're going to add up to 2. And so we could say that there's just a single microstate associated with rolling a 2 here. Whereas what if I want to roll a 3? Well, if you want to roll a 3 here, you've really got two options. Either the first die is a 1 and the second one is a 2 and they add up to 3, or the first one is the 2 and the second one's the 1 and they add up to 3. And those are your two options. And so all of a sudden now we'd have two possible microstates. And so if this were some sort of physical system, what we'd ultimately say is that, are we more likely to exist in this one of these microstates or in this microstate? Well, there's two microstates here. There's only one microstate here. The odds are double that you're going to look like this. One of these two then look like this. And these are equivalent. In either case, you've rolled a 3. So they're equivalent microstates. So, and in this case, you've got twice the odds of rolling a 3 as compared to rolling a 2. And it just leads to more microstates. And that's what's ultimately, again, behind that second law of thermodynamics, is you're just getting greater and greater probabilities when you've got more equivalent microstates for a system. So what if we talked about rolling a 7? Well, if you want to roll a 7, you're either going to have like a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. And all of a sudden, there are 7 different possible combinations on 2 dice for which you can roll a 6. That would correspond to 7 microstates, and that would be even greater probability in that case. And it turns out, if you want to roll a 7, there are 7 out of 36 possible chances to roll a 7. Whereas if you wanted to roll a 3, you only had 2 out of 36 chance. When if you wanted to roll a 2, you only got a 1 in 36 chance of that being possible. And that's ultimately all we're talking about. Now, in terms of entropy, the fewest number of microstates you can ever have is just 1. Because if you have 0 microstates to represent a particular macrostate, then that macrostate doesn't really exist. So the fewest you can have is 1. And if you've got 1 microstate for a given macrostate, let's say, well, the natural log of 1 is 0, and we just say the entropy of that system is 0. And it turns out it can't be lower. There's no such thing as having a negative entropy. Now, you can have a negative entropy change, so at least for the system or the surroundings separately, but for the whole universe, for a spontaneous process, I realize it's got to be positive. So, but while the change can be negative, the entropy itself cannot be lower than 0. It can't be negative. So the lowest it can be is 0, and that's when you've got just a single microstate. And as you increase the number of microstates, it will indeed go up. So, and have a higher entropy associated with it. And so if you look at the, transitioning from a macrostate that's described by a fewer number of microstates to a macrostate that's described by a greater number of microstates, that's going to inherently involve an increase in entropy according to this lovely formula. So that's all that's really behind that second law of thermodynamics. And we could say that, systems tend to have more disorder and stuff like that. So, but at its base, it's really just about probabilities. So more disordered systems tend to have more equivalent microstates, which is why they have more entropy. So we want to conclude this lesson talking briefly about heat engines and the Carnot cycle. And so a heat engine just takes care of the natural tendency of hot objects to transfer heat to cold objects and not the other way around. So we're going to have a hot reservoir at a higher temperature and a cold reservoir at a cold temperature, and heat's naturally going to want to get transferred between the hot and the cold. Well, what we're going to do is we're going to stick a heat engine in between, and it's going to take advantage of that tendency and use some of the energy coming from the hot reservoir to do some work instead. So not all the energy from the hot reservoir gets transferred to the cold. Some of it is going to do some work, and the more work we can get out of the heat that's coming in, so the greater that thermal efficiency. And it turns out we're never going to get 100% thermal efficiency, as we'll see. So, but we'll see some characteristics of how we might increase the thermal efficiency and things of this sort in a little bit. So, but you can see that energy comes into the heat engine on only one way, shape, or form, that's QH, but it leaves in 2 different ways, either being work done by the engine on the environment, or by heat being transferred to the cold reservoir. So we can come up with an expression here that QH is going to equal work done by the engine plus QC. Now, technically, you can run this entire process in reverse, with an example being a heat pump, like a typical air conditioning unit or like in the inside of your refrigerator. And what you can do is actually do work instead of getting work out of a heat engine. So you run the whole process in reverse, and you're going to put work in and then transfer heat from the cold to the hot. So by putting work in, you're going to run the whole thing in reverse. So and so in such cases, whether or not, QH and QC is positive and negative and stuff, because you can run reverse, it gets a little confusing. And what we're going to do here is we're just going to put some absolute value brackets on this and then come up with an expression for the work done by the engine, or in some cases done on the engine. So, and it's just going to equal QH absolute value minus QC absolute value, just essentially subtracting that to the other side. And so the difference between the heat coming from the hot reservoir and how much then you send off to the cold reservoir, any left over is going to do work by that engine. That's effectively what this is saying. So we've now got our expression for the work done by that energy. So, and then we can come up with an expression for what we call the thermal efficiency, represented by the Greek letter eta here. So in that thermal efficiency is a ratio of the work done by the engine relative to the amount of energy coming off that hot reservoir. So the greater the fraction of the energy you're pulling off that hot reservoir, that's kind of your energy cost, if you will, the greater the fraction of it that can go towards work being done relative to how much is being transferred to the cold reservoir, you're getting more work per energy cost, if you will, and that's why this is a measure of thermal efficiency. And the highest this can go theoretically is to 1. If all the energy pulled from the hot reservoir is turned into work, which turns out is impossible, as we'll see. But if it were, then you'd get a thermal efficiency of 1, can't theoretically be greater than that. And so thermal efficiency of 1 would correspond to 100%. And like I said, we're going to see that's just not physically possible. We'll talk about maybe theoretically possible, but not actually possible. All right, if we kind of substitute our expression in here for the work done by an engine, we'll have QH minus QC all over QH. So, and then we can divide both these terms by the QH to get 1 minus QC over QH. So, and there's an expression for our thermal efficiency. Just another way of looking at it. And so here, obviously I want to subtract off as small a term as possible to get to as close to 1 as possible. And that's going to happen as the amount of heat going to the cold reservoir goes to zero. The closer I can get that to going to zero, the amount transferred there from the engine, so the closer we're going to get to an efficiency of 1. Well, it turns out it's never going to quite go to zero, and we'll see why here when we take a look at the Carnot cycle. So now we'll take a quick look at the Carnot cycle. And the Carnot cycle is a description of what's going on inside a Carnot engine, which is kind of like a theoretical most efficient engine possible. And the idea is that, if we want the most efficient engine possible, then we want to do as much work as possible by that engine based on the amount of heat being drawn off that hot reservoir. Well, if we lose any heat to the surroundings, that's going to, minimize that efficiency because we want as much of the heat as possible, again, doing work. And so envisioning this kind of most efficient engine possible with no loss of heat to the surroundings, we're going to find out that we still have limits. You're never going to be able to get to 100% efficiency or a thermal efficiency of 1, if you will. So we'll see what's kind of going on here. So we're going to start with a gas under certain conditions, an ideal gas, and we're going to first undergo an isothermal expansion. And so this is going to be what we call an isotherm, going from point 1 to point 2, but the volume is getting bigger. So and the temperature at which that's carried out is going to be TH, so the hot reservoir. So, but for a gas expanding isothermally, so typically as a gas expands, it cools. So if its temperature is going to remain constant, we're going to have to allow the absorption of heat. And so on the bottom of this cylinder, we're going to have a thermally conductive material. So that allows for the absorption of heat from the hot reservoir here into the engine. So and we'll call that QH, like we did kind of on the other model for a heat engine. All right. From there, we're going to replace the thermally conductive material with one that's thermally not conductive on the bottom of the cylinder. So, and then do an expansion. So, and now because there's no heat allowed in or out, it's going to be an adiabatic expansion instead. And so we did an isothermal expansion at a temperature TH, but now we're going to do an adiabatic expansion. And again, a gas tends to cool as it expands. And so if you're not allowing any heat in or heat out, then it is going to cool and it's going to reduce its temperature down here to TC. So we're now at a lower temperature. Notice temperature is not actually on this graph, but this right here is what we call an isotherm. It keeps the temperature constant all the way along that pressure volume curve. So, and now we're at this new temperature, and now we're going to reverse the cycle. And so now, instead of doing expansions, we're going to do compressions. And the first part of this compression we're going to do is going to be an isothermal compression. So at this new temperature TC. And once again, so as a gas expands, it tends to cool down. Well, when a gas is compressed, it tends to heat up. If you're going to keep this gas from heating up, it's going to have to be allowed to lose some heat. So to some sort of cold reservoir, the amount of heat it's going to lose, we're going to call QC. And then we'll hit point 4 right here. And then to get back to point number 1, we'll once again replace the bottom of that cylinder, that bottom surface, with once again a thermally non-conducting material and do an adiabatic compression the rest of the way. And so that's our 4-step process: an isothermal expansion, followed by an adiabatic expansion, followed by an isothermal compression, followed by an adiabatic compression, getting us right back to where we started. And it's just a complete circle over and over and over again. So, and if you recall, on a pressure volume curve, the area, or pressure volume graph here, the area under the curve was the amount of work done. And so in this case, we got a certain amount of work being done under the curve. So here, but then the amount of work we got to put in to compress the gas back is under here, and it's the difference between the two that is the work being done by the engine, and that's going to kind of be highlighted by the area shaded in between all these curves. That is the work that can be done by the engine. All right, so let's take a look at a couple of things. So again, on the adiabatic processes, these two right here, so Q is 0. So, and that's by definition, adiabatic, fully insulated, no heat in, no heat out. Well, if Q is 0, if you recall, we said that delta S equals Q reversible over T, and that's why we came to the conclusion that if Q is 0, then for an adiabatic process, delta S was going to be 0 as well. So for the isothermal expansion and the isothermal compression, though, Q is not 0. So, and if you recall, we went over that on the previous page here. So we said for the actually I've got it right on this page and summarized here as well, but on the previous page we also covered that for an isothermal expansion, Q is equal to nRT natural log V final over V initial, which in this case is going to be nRT, where this is TH specifically, natural log of V2 over V1. So, and then for the isothermal compression right here, Q is going to equal nRT now at the cold temperature times natural log of V final over V initial, so V4 over V3. And then we can derive an expression for delta S for both of these as well. So, and delta S is just Q reversible over T, so we'll just divide the temperature out at which these isothermal processes were carried out. And so we're going to get nR natural log of V2 over V1. And down here, nR natural log of V4 over V3. Now here's the deal. There's nothing that says that QH and QC have to be equal to each other, and in fact they typically aren't. So, but delta S here and delta S here do have to be equal in magnitude, opposite in direction. And why is that? Well, again, if delta S is 0 here and here, and 0 for the entire cycle, well then the delta S here and the delta S here, even though they're non-zero values, so have to be equal in magnitude, but just opposite sign. That way they still add up to 0 for the entire cycle. So again, we said this is entropy is a state function. As long as we get back to point number 1 here, so delta S is going to be 0. So that's kind of the idea here. So what we can see from this then is that we've got n number of moles R, but we've got a different set of ratios here, ln of V2 over V1 and ln of V4 over V3. And what this means then is that this ratio of V2 over V1 and this ratio of V4 over V3, ultimately those ratios have to be the same. Now, V2 doesn't have to equal V4 and V1 doesn't have to equal V3, but the ratios do have to be the same. So in magnitude anyways, so one of them is going to be the inverse, it turns out, for one to come out positive, one to come out negative, but the magnitudes are ultimately going to be the same. Okay, so what's the significance of this? Well, if you go back now and look at QH and QC and realize that N is the same, R is the same, and the natural log of these ratios is the same, one positive, one negative, but the same otherwise. So then the ratio of QH to QC or QC to QH is really just a difference in temperature. And so we can say that QC is to TC as QH is to TH. And so this ratio of QC over QH is equal to TC over TH, the temperature of the hot and cold reservoirs. And so we can come up with a new expression for the thermal efficiency of a Carnot engine, not expressed in terms of the heat transfer, but expressed in terms of the temperatures of the hot and cold reservoirs. And so here we'll get 1 minus TC over TH. And so it turns out our thermal efficiency for that Carnot engine is really all about the temperature difference between the hot and the cold reservoir. And so it turns out if you want to get a higher thermal efficiency, well then you want this ratio again to get smaller and smaller and smaller. And the way they get smaller and smaller and smaller only happens as the cold reservoir approaches 0. So if you can get your cold reservoir down to an absolute 0 Kelvin temperature, which is theoretically something we can talk about, but in practice not something you're ever going to quite achieve, then you'll approach a thermal efficiency of 1, because it'd be 1 minus 0, right? So, okay, the other thing you can do here though, so if you're really never going to get this cold reservoir temperature down to 0, but what you can do is make the difference in these temperatures as large as possible. The bigger the difference in these temperatures, the smaller this fraction is going to be, and so you're going to be subtracting a smaller fraction from 1 and ending up with an overall higher efficiency. So, but now we've got a new expression for specifically a Carnot engine, not just any heat engine, but a Carnot engine, the most efficient one possible, that expresses the thermal efficiency not in terms of the heat, but simply in terms of the temperature of the hot and cold reservoir. All right, and the last question we're going to do is simply a calculation involving this thermal efficiency, and it says calculate the temperature needed for a hot reservoir. Let's try that again. Calculate the needed temperature of the hot reservoir of a Carnot engine operating at 25% efficiency if the cold reservoir has a temperature of 298 Kelvin. All right, so we want a thermal efficiency of 25%. That corresponds here to 0.25, and that's going to equal 1 minus cold reservoir's 298 Kelvin all over the temperature of a hot reservoir. And do a little algebra here, and we'll subtract 1 off to the other side. So we'll get 0.25 minus 1 equals, don't forget the negative, I almost did, 298 Kelvin over TH. So 0.25 minus 1 is negative 0.75. and that's equal to negative 298 Kelvin over TH. So we'll multiply by TH and divide by negative 0.75, and we'll get TH equal to negative 298 Kelvin over negative 0.75. Let our calculator do the heavy lifting for us. Negative 298 divided by negative 0.75 is 397.3333, and to 3 sig figs, we'll round that to 397 Kelvin. Cool, so it turns out, like on your car engine and things of this sort, your cold reservoir is just the surrounding temperature in the environment around you. The hot temperature, though, is the heat or the temperature of the engine itself. And so it turns out the hotter you run your engine, the more efficient it gets. And you might ask, well, why don't we heat up our engines a whole lot hotter? And that is due to the limitations of your engine oil. So at some point, your engine oil is going to break down and no longer act as a sufficient lubricant. And you might just throw a rod right out of the side of your engine block, like I've done on occasion. If you have found this lesson helpful, consider giving it a like. Happy studying.